Okay, so it's a pleasure to introduce Manuel Cuerno, and he's going to talk about filling radius and reach of isometrically embedded metric spaces.
So thank you very much, and thank you to the organizers for this invitation. So I will talk about filling radius and reach of isometrically embedded metric spaces. My talk will be will have two clear parts. And well, I will also want to say that I am a PhD student, and my advisor is Luis Guijarro. This is the index of my talk. First, I will recall the definition of the filling radius and explain some of the most significant results. Then I will show some of my results involving submersion and submetries and lower bound for the value of the filling radius. And lastly, I will show the reach of the Kuratowski embedding. This will allow me to pass to the second part of the talk, where I will talk about the Wasserstein space and the reach of the Wasserstein embedding. Okay, so of course, if anyone has any question during the talk, please interrupt me and ask me. So in the talk, M will be a compact Riemannian N manifold, and dm will be its distant function. We can see the distant function with a fixed point as a function in L infinity of M, which is the set of all the real valued function with the supremum norm bounded. There is a canonical inclusion called the Kuratowski embedding, where we can send each point in the manifold to its distant function. Indeed, it is an isometric embedding, and it is known as the Kuratowski embedding. Moreover, I'm not going to show or talk about this in the talk, but L infinity is a very huge space, and indeed we have like an infinite isometric copies of the manifold into L infinity. It's a very interesting space. A little bit more of notation: given r greater than 0, we will denote UR as the R neighborhood of M in L infinity, and iota R the inclusion. Then, of course, if we fix an F coefficient ring, we can have the induced homomorphisms in the N homology of iota R in the homology. So now we can find the filling radius. So the filling radius of M is the infimum of those R greater than 0 for which the fundamental class vanishes in the iota application. A more geometrical perspective of this: imagine a compact N manifold captures an n+1 dimensional hole. Imagine the N sphere, we have an n+1 dimensional hole inside the N sphere. So when we put the manifold into L infinity, and we do these tubular neighborhoods of the manifold, we want to know the infimum of the values for which these neighborhoods collapse the hole inside. So that's the reason why the name is like filling radius, because we want to fill the hole inside the manifold. This definition was due to Gromov, and the first result also to him. So if M is a closed manifold, then the filling radius is less or equal than a constant for the times the n square of the volume of the manifold. Also in the same year, a student of Gromov, Katz, proved that if M is a closed connected manifold, then the filling radius is less or equal than 1/3 the diameter of M. Later, Fred Willem gives some, in a very beautiful paper, shows some estimations of the filling radius of the positively curved manifolds. So if we have a positive curved manifold, then its filling radius is less or equal the filling radius of the sphere. If the filling radius of M is the same as the filling radius of the N sphere, then M is isometric to the sphere. There exists a delta dependent on the dimension. So if the filling radius of the sphere minus delta is less than the filling radius of the manifold, then M is diffeomorphic to the sphere. And last, if the filling radius is greater than pi/6, then M is a twisted sphere. In 2013, Jokota replied more or less the same result as Fred, but in the case of Alexandrov spaces. Well, lastly, it's not on the slides, but there are two last results. One is due to Nabutovsky, another one is due to Facundo Memoli in a context of topological data analysis, and he used the filling radius for some computations. Now, the filling radius it's a hard invariant because it's very difficult to compute it. We only know the exact value of the filling radius of the sphere.
Sorry, Manu.
Yes.
Yeah. So in the previous slide, sorry, what's a twisted sphere here?
A twisted sphere is you glue two disks, but the identification in the boundary is not the identity.
I see. Oh, okay. Thanks.
Okay, so we know the value of the filling radius of the sphere due to Katz. Filling radius of the real projective plane. We know the filling radius of CP1 and CP2. We know the exact value of CPN, but where the coefficient we are using set and set2 as the coefficient ring. And when we change to Q, we can compute the value of CPN. All these results are due to Katz, and there are very difficult papers with very tiny details. And then we have all these inequalities. The conjecture is indeed that the value of the filling radius of CPN is indeed 1/2 arccosine of -1/3. Okay, so this has been a very fast overview over the filling radius literature. So now my advisor Luis and I have produced some bounds for the filling radius. The first one have the submersion, the Riemannian submersion involved on it. So first I recall the definition of Riemannian submersion. A differentiable map pi is called a submersion if pi is surjective and the differential has rank n. Moreover, if M and B are have Riemannian metrics, the submersion is said Riemannian if it preserves the lengths of the horizontal vectors, the vectors orthogonal to the fibers. So if I is a Riemannian submersion between two manifolds, then the filling radius of the base of the total space is less or equal of 1/2 times the maximum of the diameters of the fibers. We can generalize this with the notion of the submetry. The submetry between metric spaces is an application such that for every P in the total space and any closed ball P center on P of radius r greater than 0, then this ball is mapped onto the ball with the center pi of P and the same radius. As it is shown in the slide, this is a purely metric version of a Riemannian submersion. And we have this result due to Bertowski and Guijarro. Then if phi is a submetry within Riemannian manifolds, then this phi is a C11 Riemannian submersion. So we can, here we have a notion of generalization of submersions, but for metric spaces. So a corollary of our result is that the X is a metric manifold, a closed manifold with a distance, and Y is a metric space, and we have a submetry between them, then the filling radius has the same bound. We have more or less the same bound if we have a graph product, and we have the same result if we have a singular Riemannian foliation. Now, I have shown an upper bound. I'm going to show now a lower bound. Firstly, I want to recall the definition of injectivity radius. For a Riemannian manifold, and every point in the manifold injectivity radius at P is the supremum of r greater than 0, such that the exponential in that ball is a diffeomorphism. And we can define the injectivity radius of the whole manifold as the infimums of the injectivity radius. So in this theorem, firstly shown by Green and Peters in 1992, and with we gave a different proof in our paper, we show that if M is a closed Riemannian manifold with injectivity radius, that quantity, and sectional curvature less or equal than delta with delta non-negative, then the filling radius is greater or equal than 1/4 the minimum of the injectivity radius, or pi over the square root of delta. So as I have said, Professor Guijarro and I gave a different proof than Green and Peterson, and with more details, and we tried to show that this filling radius is really related with how much we can enlarge the R neighborhood of a manifold, such that every point in L infinity we can find an unique projection onto the manifold. And with this perspective, we found this bound. Well, a funny fact is that we combine both inequalities, and pi is a Riemannian submersion between closed manifolds. Then we have this interesting inequality. Okay, so as at the beginning of the talk, I showed the Kuratowski embedding, and I explained the Kuratowski embedding is an isometric copy of the manifold into L infinity. Some of our aims was trying to study more in detail the Kuratowski embedding and some of the properties we have on it. And when we were with the last inequality, with this inequality, and we were fighting with these unique projections, we realized that the reach, in the sense of Federer, also measures if it exists an R neighborhood with unique projections. So we tried to compute the reach of the Kuratowski embedding. First of all, for all the people who don't know what the reach is, I'm going to explain here. So if X is a metric space and A is a subset of X, we define the set of points having a unique metric projection in A as this. The unique points of A are the points in the metric space such that there exists a unique point in the subset such that the distance from the point to the subset is equal to the distance to the point X to the point A. Then we can locally define the reach as the supremum of R is greater than 0, so that if we construct balls with center A and radius R, these balls are completely inside the unique points of A. A funny fact is that these unique points of A also contains the subset A, because if X is a point in A, then the distance of A to capital A is realized when A is with A is X and X is A. So these points has a unique projection. Okay, so these unique points of A, it's not an empty set. At least it's not an empty set. Finally, we can globally define the reach as the infimum of all the local reaches. Okay, so an easy example is we can think about S1 into R2. In S1 in R2, all the points have a unique projection instead of minus the center, minus 0, 0. The point 0, 0 has infinite projections in S1. So the reach of S1 into R2 is 1. But if we have the disk, so it's S1 all filled, the reach of the disk is infinity, because every point in R2 has a unique projection through the set. Okay. An easy remark is that if M is a submanifold of Rn, then the reach is greater than 0. We can always find a neighborhood around every point such that the reach is 0, is greater than 0. And the surprisingly result we found was that if M is a compact Riemannian manifold, then for every point in the manifold, the local reach of the point is 0. After showing you the proof, I want to present you some questions that we nowadays have about this surprisingly fact. So we firstly think, okay, what's the unique points of M into L infinity only M? But well, no, because this kind of functions that are in L infinity, but not in the isometric copy of M, are in the unique points of M. So the next question we haven't solved yet is these unique points of M in L infinity dense? So now I'm going to prove theorem 7. The proof of theorem 7 is a very easy metric proof. So we are going to check for every function in the manifold and every epsilon greater than 0, there exists a function in the ball such that it has at least two barycenters. The people who knows the literature, it has two barycenters, two unique metric projections. Okay, so F has two unique metric projections. This ball is not uniquely contained into the unique points of M. So for that reason, the reach of the point at every point will be 0, and the reach of the isometric copy of M will be 0. Okay? Any doubt, any question?
I don't think so. Not so far.
Okay. Yeah. So, firstly, we consider a delta greater than 0, such that delta is less than epsilon, and some q in M with the property that the distance in M from P to Q is equal to delta. Then, as we are in the isometric copy of M, the distance of the distance between D and DQ will be delta. So our candidate of function F will be 1/2 distance through P plus distance through Q. And now we have only to prove 3 easy claims. The first, that this function is not in the isometric copy, but if F is a point in the isometric copy of M, then the distance F of R will be the distance of R to R, so it will be 0. But this quantity is greater than 0. Secondly, we have to check the distance of F through D and the distance of F through D2 is the same, but for that reason, we pick the medium point between the two functions. And lastly, there does not exist another distance function in the isometric copy closer to F than D2. But applying straightforward the triangular inequality, we obtain a contradiction. So we have proved that the reach of the isometric copy of the manifold into L infinity is indeed 0. This part of the talk was based on this paper that my advisor and I wrote, that is called Upper and Lower Bounds on the Field Radius. I think accepted in Indiana University Mathematics Journal, and it's available on archive. And the next part of the talk will be based on this following preprint between Jaime Santos Rodriguez, Javier Casado, and I, that it's called On the Reach of Isometric Embeddings into Wasserstein type spaces. Why these two parts of, why this is one talk and no two talks? Because when we finished our first paper, Javier Casado, Jaime, and I began to think in the reach in other spaces where we have isometric copies of our manifolds or our metric spaces. And of course, one of the first examples we thought were the Wasserstein spaces. First of all, I will give the definition of the Wasserstein space. So if X is a metric space, a measured metric space, we can denote calligraphical P of X as the set of probability measures of X, and calligraphical P to P, the ones with finite moment. I mean, the ones with this integral bounded. Moreover, we can define a transference plans between two positive measures, mu and nu, as a finite measure I, which satisfies the following conditions, that the marginals are in mu and nu. So we can define the Wasserstein distance, the P Wasserstein distance between these two probability measures as the minimum between all the transference plans of this integral. This distance, it might seem as a very abstract one, but it appears in an optimal transport problem. And well, we can define the Wasserstein space of the space of the probability measures with I finite moment with this distance. We have these two piles of sand, the pile of sand mu and the pile of sand nu. And they have like the same amount of sand. In this case, as they are probability measures, the amount of sand is 1. And we're going to know how to move the sand between mu and the sand between, we want to know how to move the sand in mu to the whole nu. So, for example, we can take the point X to the point Y, or we can take the point X between Y, we can split X between Y and Z. This optimal transport problem is computed by the Wasserstein distance. So it is a very, like how to say, a very graphical meaning of the Wasserstein distance, this pile of sands, courtesy of Jaime Santos. So now, what's the matter with the Wasserstein space? So in the Wasserstein space, we also have an inclusion that is an isometric embedding, that we can send the point X to the probability measure delta of X. So the natural question is, what is the reach of a metric space into the Wasserstein space? It is always 0, as in the L infinity case. So from now on, I want to have this remark of notation. We are going to denote X in the metric space as barycenter of mu if the Wasserstein distance of mu through X is the same as the Wasserstein distance of X of mu to delta X. Okay, we will say that this metric projection we will call from now on barycenter. This is the name that it is that you can check in the it's most common in the literature about this area. So first of all, answering one question, one of the open questions we have on the case of L infinity in the Wasserstein space, this is non-branching, the unique point sets is indeed dense. So it is a very straightforward proof. So if mu is a measure in the Wasserstein space with X its barycenter, we will take a measure nu inside the geodesic between delta X and mu. Now suppose that there exists some other point set in our metric space that is a barycenter for mu. This will imply that the Wasserstein distance between mu, nu, and delta Z will be less or equal than the Wasserstein distance between nu and delta X. And applying the triangular inequality, we will also have that mu, the distance between mu and delta Z will be less or equal than the distance of mu and delta X. So Z will also be a barycenter for mu, sorry. So here we have the contradiction because this will be a branching geodesic joining mu and delta Z. And the Wasserstein space of a non-branching metric space is non-branching. So mu is a measure in the unique points of X, and we can take arbitrarily close to mu. And with that, we prove that this space is then in the Wasserstein space. So now we have some hope for the possibility of positivity of the ridge. But well, our hopes will list very little, because we found this proposition that if X is a geodesic metric space and we have 2 points in this space, we consider the probability measure mu as the segment for some delta, a point in the segment for some delta. Then mu realizes its p-Wasserstein distance for greater than 1 to exactly 1 for every minimizing geodesic between X and Y. So if, for example, imagine the sphere, and we take X as the North Pole and Y the South Pole, and we pick any point in the segment between these 2 poles. So as we have infinite minimizing geodesics between the North Pole and the South Pole, any point in the segment realizes its distance in infinity many points in the manifold. I will show the proof a little bit fast, but well, in the preprint there are all the details available. So imagine gamma is a geodesic between X and Y. Then the p-Wasserstein distance between delta of any point in the geodesic and mu. Remember, mu is a point in the segment. This has this shape. We can take out the distance between X and Y, and we have this quantity depending on t. It's the variable on the geodesic and lambda. Remember that lambda is fixed. So now we want to minimize this quantity. For that, we can take the derivative in t, and well, as in calculus 1, no? And we found that this 0 is the quantity where the derivative is 0. In the paper, we prove that in this value, this quantity is indeed a minimum. And we have this huge expression. But what is the important point in this expression? So the important point in this expression is that this expression is independent from the minimizing geodesic we have chosen. So now we only have to prove that the minimum can only be achieved inside a minimizing geodesic. We will choose any point in the metric space, and we will construct another point inside the minimizing geodesic, verifying this inequality. Okay, so that the point in the geodesic is less the distance through mu. The distance to mu from the point in the geodesic is less or equal than the distance of the point in the metric space. So, for proving this, we have split the proof into cases. The first case is that the point A, the distance from A to Y is greater or equal than the distance of X to Y. And this is straightforward. So if we choose X as the point in the geodesic, we have the desired inequality. We have the same. Now we have the other part, and we can pick A inside the geodesic at distance this quantity to Y, because we can arbitrarily choose this point. And well, if you observe only all these computations, we indeed have the desired inequality. So the important thing is that this segment point, has any realizers as geodesics exists between X and Y. It seems like a very, I don't know, like very not much important proposition, but indeed with this proposition, we can prove the following important result. If X is a geodesic metric space and X is a point in X, such that there exists another point Y with the property that it exists at least two different minimizing geodesics from X to Y, then for every P, reach in this point will be 0. In particular, if there exists a point satisfying this property, then the reach will be 0 in the whole space. So, which spaces holds this property? We have a lot of examples. If M is a compact manifold, then this manifold holds this property. M is a not simply connected manifold complete, then we have the same property. Now, if you have seen, we are always working with P greater than 1. Why is that the reason? Why that reason? Because if we fix P equal to 1, any metric space has reached 0. The proof is the same as in the L infinity case. Lastly, well, we can think, so all this talk for the same result as in the L infinity case? No. We have cases in the Wasserstein space where the reach is positive. Indeed, it's not only positive, it's infinity. We obtained these examples working with Martin Kell's paper, and we have to impose some restrictions in the distance to the distance function of the metric space. And after applying all these results, we obtain that if X is a cat-zero space, then the reach of this space is infinity. And as an example of a cat-zero space, if M is a Hadamard manifold, the reach of the manifold is also infinity. So finally, and now we have, I think, like a lot of time for questions. Where are the further questions? So first of all, we want to think any manifold that does not hold the property of the two minimizing geodesics. So we want to think what happens with the manifold without conjugate points. And nowadays, we haven't found any example of a manifold that there exists some constructions of manifold with conjugate points, but that are outside all the examples we gave on the paper, but we don't know yet the reach of those manifolds. I think those manifolds appears in a Gulliver paper. I don't remember the name yet now. Then so that's one. This is very related with this following question, that if there exists any space with positive reach but not infinity, and we think that if any such space exists, this will be a manifold without conjugate points, but we are not sure yet. We haven't found anything. And finally, we are trying to work with to compute another reaches, but now we want to prove things in sets in spaces of spaces, such as the Gromov-Hausdorff of space, the Wasserstein Gromov-Hausdorff, and things like that. So I think perhaps I've been a little bit fast, but now we have time for a lot of questions. So thank you for your attention.
Thank you. All right, thank you for this very nice talk. Are there any questions either here or in Zoom? Yeah, so I have a couple of questions actually. So I remember you you can embed manifolds in L infinity, like you said, but I remember there are some embeddings, like for example, in other LPs, like say L2, you can embed the manifold via the heat kernel, right? I think so. At any point, the heat kernel and start.
I don't know if this embedding is isometric.
Yeah, it's not isometric, but I think there's like at least some like if you pull back the metrics, like it merges in some way to the original metric, I think. But I guess my question is, are you pursuing this direction, or can something be done?
Well, we thought about those kind of embeddings in all2, but at the time we were thinking only about isometric embeddings.
I see. And I guess my second question is like coming back to the filling radius.
Yeah.
What's the picture for spaces which are not positively curved? Because the results you mentioned are for positively curved spaces, right?
Yeah, I'm not sure, but I don't know if there exists any result with non-positively curved spaces.
I see. Okay, thanks. Is there any other question?
I have one question. I mean, you mentioned that you want to study reach of other classes of spaces, but I think this is probably a different question, the one that I'm going to ask. If you have convergence of spaces, and is the reach like continuous or semi-continuous with respect to Gromov-Hausdorff distance or other type of distances?
That's a nice question, but now I'm not sure. Perhaps not. Imagine, I think like like a donut in R2, no? So the hole is always like smaller, and the reach is always going to 0. And when you fill the hole, you have the disk, and the reach is infinity.
Do you have applications for filling volume?
Oh, well, the filling volume, we try, but it's a very extremely difficult quantity. I think even Gromov only have conjectures about the quantity of the filling volume.
Okay, thanks. There are more questions. Yeah, we have another question from the audience, and it says, which are some applications of filling radius in optimization and data analysis problems?
The Facundo Memoli paper was about distance between spheres of different dimensions. And in that direction, he finally proved some estimations of the value of the filling radius.
I had a question about filling radius. I think you mentioned the result of cuts.
Yeah. Wait me a second. I'm going to share again the screen. Yeah. Yeah, you mean this one?
This one, yeah, that one. 1/3 of the diameter, and then, but in your results with Gihara and others about Riemannian submersions, and you had 1/2 instead of 1/3 of the diameter.
Yeah,
I was wondering why you don't have 1/3. I mean,
we weren't able.
Yeah, right. But
yeah, we weren't able to reach 1/3.
But do you think it should be true? I mean, it feels like. I mean, if you have 1/3 here, maybe you should.
Yeah, but here is the diameter of the manifold, and our result is the diameter of the fiber.
Yes, yeah, no, of course, but I understand. I mean, you kind of want to fill in the fibers, and then.
Yeah. So
it seems like you should have 1/3 here also. But
yeah. we think the same as you, but we weren't able to reach that quantity. We tried to interchange the diameter with the spread. That is another metric quantity similar to the diameter, but a little weaker. But we weren't able also to change the diameter with the spread.
Okay, all right. Thank you.
We already understood your example. So on the screen, are there any other questions? Okay, if there are no more questions, thanks again for your talk.
Okay.